Welcome to the first chapter of our Physics O-level lessons. Today, our chapter is Measurements and Units. We're going to start by understanding physical quantity. So what is physical quantity? Physical quantities are a characteristic or property of an object that can be measured or calculated from other measurements. Say for example, I have this pencil here, and I say that the length of this pencil is 12 cm. Now the length of the pencil is its physical quantity or property that can be measured or calculated from other measurements, which is in this case 12 cm. So length is basically a physical quantity of this pencil, which then can be measured or calculated from this measurement 12 cm. In the same way, we have mass, volume, density, weight, and many more physical quantities of a particular object. So this is what physical quantity is. Now we're going to understand about measurements. So measurement is an assignment of a numerical value to a physical quantity. Say for example, 5 grams is the mass of this pencil. It basically represents a physical quantity of this pencil. What is the physical quantity? The mass. Mass is a physical quantity. Length is also a physical quantity, just like we read before here. In this section, we have mass, volume, density, weight, and many other physical quantities. So measurements are basically what calculates these physical quantities. So for example, the mass of this pencil is 5 grams and the length of a pencil is 12 cm. So these are the measurements calculating the physical quantities of this pencil. Now, as it can be seen, a measurement is always in two parts. One is the number part and the other is the unit part. And both these parts are necessary for a measurement to be complete. For example, if I say that the length of this pencil is centimeter, of course we will not be able to understand what I'm trying to say until and unless I place a digit behind the centimeter. In the same way, I cannot just write a number and call it the pencil's length. I need to put a unit at the end to complete the measurement. So, speaking of units, let's check them right now. Units of measurement. Units refer to a quantity of a constant magnitude used to measure the magnitudes of other quantities of an identical type. So in simple words, units are defined as the reference standard used for measurement. So here we have some units written down here. For example, for mass we have grams, milligrams, kilograms, and etc. So these are the units that are basically standardized to measure a specific quantity of mass. So now let's look at this SI system of units. The International System of Units, also called SI, is a standardized system of measurement used in science, industry, and commerce around the world. The SI system is based on the metric system and provides a universal and consistent system of measurement for physical quantities. In the SI system, there are two types of units: the base units and the derived units. So here we have a table of some basic physical quantities and their base units. Base units are the fundamental units of measurement in a system of units. These units are used to define and measure physical quantities. So there are total 7 base units, which I have all written down over here in this table. First we have mass, which has a base unit kilogram. The symbol of this unit is kg. Length has a base unit meters, symbol m. Time measured in seconds, symbol s. Temperature measured in Kelvin, symbol capital K. Electric current measured in amperes, symbol capital A. Pressure is measured in atmospheres, which has a symbol pascals. Amount of substance is measured in mole, symbol mole. Luminous intensity is measured in candela, which has a symbol CD. Now, these base units are important to remember as they are the fundamental units of measurement in a system of units. These are the units that basically are used to define and measure physical quantities. And from these base units, we get the derived units, which are the second types of units in the SI system. So, derived units are units of measurement that are formed by combining two or more base units. These units are used to measure physical quantities that cannot be expressed in terms of a single base unit. And here is a table of some physical quantities and their derived units. So basically, derived units are units which are used to measure physical quantities that cannot be expressed in terms of a single base unit. It's not necessary that a derived unit is supposed to be made of only base units. It can be made up of derived units as well. For example, density is made up of gram per centimeter cube. So centimeter cube is a derived unit of volume, and grams is a base unit of mass. Now let's read some of the physical quantities and their derived units in this table. Now there are many different physical quantities with their derived units. I've just written down a few of them here. Firstly, we have volume, which is measured in centimeter cube. The symbol of this derived unit is cm with a small 3 above. Overall, we read it as centimeter cube. Now this derived unit is made up of 3 base units. Okay, so for example, I have a cube here and I want to measure the volume of this cube. So I would basically measure the width, height and length of this cube, all in centimeters, and multiply all of them to get an answer in centimeter cube. So when we multiply 3 centimeters, we get a centimeter cube. So basically, centimeters multiplied by another centimeter and another centimeter are 3 base units multiplying to form a single derived unit. So volume was an example of a derived unit. Then we have density, which has a derived unit gram per centimeter cube, symbol G/cm cube. Now this derived unit is made up of one derived unit and a base unit. Grams is a base unit of mass, but centimeter cube is a derived unit of volume. So for example, if I want to find the density of this cube over here, I would divide the mass of this cube with the volume of this cube to find the density. So basically what I'm doing is dividing grams with centimeter cube, and so I get a derived unit which is gram per centimeter cube. So this was density. Then we have velocity, which has a derived unit meter per second. Now this derived unit is made up of base units only, 2 base units. One is meter and the other is second. One is the base unit of time and the other is the base unit of length. Then we have acceleration, meter per second square. And lastly we have force, which is measured in newtons, symbol capital N. Now make sure you don't confuse this newton with base units, as it is not a base unit. It looks like one, but actually the derived unit of force is too long to write down. So they have shortened it down to Newton, who was a scientist who discovered force. So Newton is not a base unit, it is a derived unit. Now that we've understood base units and derived units both, as well as the SI system of units, we can move ahead onto the metric system of units. So, the metric system is a system of units for measuring length, mass, volume, and other physical quantities. The metric system is based on the decimal system with units that are related to each other in multiples of 10. The metric system also includes prefixes that indicate multiples or fractions of the base units. Now let's understand what we're trying to talk about here. To understand the metric system of units, we have to understand prefixes. So what are prefixes? Prefixes in units are used to indicate multiples or fractions of the base unit of measurement. So in the metric system, prefixes are added to the base units to indicate larger or smaller quantities. So here are some common metric prefixes and their meanings. Prefixes are basically added to the base units to indicate smaller quantities or larger quantities. So we have a base unit, meter for example. if I want to make this meter 1000 times bigger, then rather than writing 1000 meters, I would simply write 1 kilometer. Because what kilo means is 1000 times the base unit. So I basically put this prefix behind the base unit meter and I get kilometer, which means 1000 times the base unit. In other words, 1 meter multiplied by 1000 is 1 kilometer. So adding this prefix made the base unit bigger. In the same way, we can make a base unit smaller using these three prefixes. Milli, for example, if I put this prefix, it would mean 1000th of the base unit. What 1000th of the base unit means is that if I divide 1 meter into 1000 parts, that 1000th part of the meter would be called a millimeter. If I say milligrams, I'm basically dividing a gram into 1000 parts, and that 1000th part is going to be a milligram. In the same way, we have micrometer, which means 1/1,000,000th of the base unit. In other words, if I divide a meter or any base unit into 1,000,000 parts, that one part would be called a micrometer. Nano means 1/1000,000th of the base unit. Mega means 1,000,000 times the base unit multiplied by 1,000,000. And giga means 1 billion times the base unit multiplied by 1 billion. So these were the common metric prefixes and their meanings. Now we're going to understand the conversion of units. Basically, how can we convert a specific unit into a different unit? For example, kilo into milli. If I want to convert kilograms into milligrams, how would I do that? Now, this conversion of units helps us in different cases. For example, if I'm baking a cake and the recipe I'm given is in pounds, but the scale I have to measure the ingredients of the cake shows me the measurement in grams, then I would need to convert the recipe of pounds into grams in order to make it. So, in this case, I would have to convert pounds into grams. So, conversion of units refers to the process of changing a quantity expressed in one unit of measurement into an equivalent quantity expressed in another unit of measurement. And this is typically done by multiplying or dividing the original value by a conversion factor, which is a ratio that expresses the relationship between the two units. And here we have a table of some conversion factors: length, time, and mass. So let's read them out. 1 kilometer is a unit of length, and this kilometer is equal to 1000 meters. This we have known before as well, because kilo is a prefix which is equal to 1000 times the base unit, and 1 meter is equal to 1000 millimeters. So the conversion factor is that 1 kilometer is equal to 1000 meters and 1 meter is equal to 1000 millimeters. So if I'm going to convert a kilometer into meters, then I would use this conversion factor, which is that 1 kilometer is equal to 1000 meters. Say for example, I have 50 kilometers here and I want to convert it into meters. So what I would simply do is multiply or divide the original value by the conversion factor. Now, the rule for conversion is that if it is a big unit than the unit we are going to convert it into, then we would multiply the original value with the conversion factor. But if it is a smaller unit than the unit we are going to convert it into, then we divide the original value by the conversion factor. So if we are converting meters into kilometers, then I would divide. But if I am converting kilometers into meters, then I would multiply. So what I would do is multiply 50 by 1000 in order to get the answer, because the conversion factor is 1000. 1 kilometer is equal to 1000 meters. So if I'm converting a kilometer into meters, I would simply multiply 50 by 1000, and what I get is 50,000 meters. Okay, in the same way, if we are converting meters into millimeters, then we would again multiply the original value in meters by 1000, because the conversion factor is 1 meter is equal to 1000 millimeters. So I would multiply the original value by 1000 in order to get the answer in millimeters. But now, say for example, I want to convert 50 kilometers into millimeters. Then what I'm going to do? If we are converting a base unit into a different unit, then it's very simple. We just multiply with the conversion, multiply or divide with the conversion factor. But if we are converting a given unit which is not a base unit into a different kind of unit which is also not a base unit, then what we do is that there are two stages involved in this type of conversion. The first stage is to convert the given value in kilometers into meters. First into meters. This is the first stage. When we convert the kilometers into meters, then we convert the meters into millimeters. So this is the difference between converting base units into a given value or given value into its base unit, or converting a different kind of unit into again a different unit, not a base unit. So for that, we first convert whatever the original value is, we convert it back into its base unit first, and then convert the base unit into the desired unit. So say for example, I have 50 kilometers and I want to convert it into millimeters. So I first convert the kilometers, 50 kilometers into meters. So 50 kilometers into meters is how much? We just took it out just a minute ago. It is 50,000 meters. Now I would convert this meters into millimeters. And for doing that, I again apply the conversion factor, which is 1000 millimeters is equal to 1 meter. So I would again multiply 50,000 meters with 1000 in order to find the answer in millimeters. So 50,000 multiplied by 1000 is 50 million millimeters. So how do we write it? 50, comma, 3 zeros, comma, and 3 zeros again. Now that's a big answer. Of course, if we convert 50 kilometers into millimeters, then it would be a big answer because millimeters is very small. Now we can see that 50 kilometers are equal to 50 million millimeters. In the same way, if we are converting kilometers into micrometers, we first convert the kilometers into meters this way, and then convert the meters into micrometers. What is the conversion factor for micrometer? This is the conversion factor. 1 million micrometers are equal to 1 meter. So then what we do is multiply again, because we are converting a bigger unit into a smaller one. So we multiply 50,000 by 1 million to find the answer in micrometers. Now say for example, I have millimeters here and I want to convert these millimeters into micrometer. Then again, because I'm not converting it into a base unit or a base unit into a desired unit, so I have two different types of units. Millimeters into micrometers. None of them is the base unit. So if I'm converting millimeters into micrometers, I would first need to convert millimeters into meters and then convert the meters into micrometer. Now, the conversion factor of millimeters and meter is 1000. 1 meter is equal to 1000 millimeters. So I would I would divide the millimeters by 1000 to get the answer in meters, because millimeter is smaller than the meter. So it's a smaller unit compared to the meter. So for converting smaller units into bigger ones, we divide. So I would divide 50 by 1000 to find the answer in meters first. And my answer is 0.05 meters. So 50 millimeters are equal to 0.05 meters. Now I'm going to convert these meters into micrometers. So the conversion factor for meters and micrometers is that 1 million micrometers are equal to 1 meter. Now because I'm converting a bigger unit into a smaller one, I would multiply. Before, millimeters was smaller than meters, so I divided. But now meters is bigger than micrometers, so I'm going to multiply. So 0.05 multiplied by 1 million is equal to 50,000 micrometers. So this is how we converted millimeters into micrometers. So it's just so simple. We have to just multiply with the conversion factor. Multiply or divide with the conversion factor. But if I'm converting the given unit into a smaller unit, smaller than the given unit, then I would multiply. And if I'm converting a small unit into a bigger one, then I would divide. So I have a conversion that doesn't involve base units at all. Say for example, millimeters into micrometers is a conversion, or kilometers into millimeters, or kilometers into micrometers. There are a lot of pairs we can make which doesn't involve the base unit. Then I would simply do the conversion in 2 steps. The first step is to convert the given unit into its base unit first, and the second step is to convert that base unit into the desired unit. So there are two stages involved in this. So for conversion, we have to remember the base units as well. So we have to remember the base unit of time in order to convert a unit into a different unit. So if I'm converting minutes into hours, I should know the base unit, because I would first have to convert minute into the base unit and then convert the base unit into hours. So minute is not the base unit, neither is hour the base unit of time. The base unit of time is the second. So for converting a minute into an hour, I would first have to convert the minute into seconds and then convert the seconds into hours, just in 2 steps. But if I'm converting a minute into seconds or an hour into seconds, then I would simply just put the conversion factor and do it. There's no 2 steps. In the same way of mass, for example, I'm converting kilograms into milligrams. For that, I would first have to convert the kilograms into grams. Okay, this is kind of confusing because the base unit of mass is not grams, it is kilograms. So this kind of can get confusing, but in conversion, we take gram as the base unit of mass. But when we read the base units, the base unit of mass is the kilograms. So you should just remember that in conversion, the base unit of mass apparently is grams. But in actual, kilograms is the base unit of mass. These are certain things that we have to just memorize to make it simple. So this is what conversion is. Now let's move ahead on to looking at some physical quantities and the tools we use to measure these physical quantities. Starting with mass. So mass is the amount of matter a substance contains. This is the definition of mass. It is highly recommended to memorize these definitions. The more you remember the definitions of these physical quantities, the easier it would be to answer questions relating to this physical quantity. And now we have some points to remember over here as well. 1. The greater the mass of an object, the stronger is the Earth's gravitational pull on it. And second is that the greater the mass is of the object, the greater the resistance to change in motion. So if there is a heavy object, it is hard to push that object. So there is a greater resistance to change in motion because it has a greater mass. Light objects are easily movable because they are light and there is less resistance to change in motion. And the greater the mass of an object, the stronger is the Earth's gravitational pull on it. So if there is a heavy object, it will have a stronger gravitational pull compared to a light object. So the SI base unit of mass is the kilograms. And for measuring mass, we use a beam balance or a pan balance. So this is what a beam balance looks like, and this is a pan balance. So this was all about mass. Now we're going to look at time. Time is also a physical quantity which has a base unit seconds, symbol small s, and we use stopwatches or stop clocks to measure time. Next we have length. The SI base unit of length is the meter, and the tools we use to measure length are the Metre Rule, tape measure, micrometer screw gauge, and lastly the Vernier Calipers. So these are a lot of tools and we're going to understand these tools right now. Starting with Metre Rule. So the Metre Rule measures up to only 1 meter and can measure accurately up to 1 millimeter. So the smallest value it can measure accurately is 1 millimeter and the largest is 1 meters. So the Metre Rule is suitable for measuring regular objects like squares and straight lines because Metre Rule is not bendable and it's not flexible. So to measure an object using a Metre Rule, we just place the Metre Rule by the object and measure its length. So for example, this cube has a length of 14 centimeters. The Metre Rule is calibrated in inches as well as centimeters as well as millimeters. But the Metre Rule cannot be used to measure objects of a greater length, say for example 2 meters. We cannot use a meter rule to measure lengths bigger than 1 meter. So for doing that, we use a tape measure. So the tape measure can be used to measure long lengths as well as smaller ones. By smaller, we mean 1 millimeter. This is the smallest value a tape measure and a meter rule can measure. To measure even smaller ones like micrometer, we use other tools like the Vernier Calipers and the micrometer screw gauge. But for now, let's stick with tape measure. The tape measure can be used to measure long lengths as well. And because the tape is flexible, it can also measure diameters of cylindrical objects or lengths of bent wires. Okay, so this was the tape measure and the meter rule. Now let's move ahead onto the Vernier Calipers. So the Vernier Calipers measures up to 1/10 of a millimeter. So if I divide a millimeter into 10 parts, the 1/10th part of this millimeter is the accuracy of the Vernier Calipers. So the calipers is used to measure small lengths, internal diameters and external diameters of pipes and tubes. Now of course 1/10 of a millimeter is impossible to be measured by a human eye because 1/10 of a millimeter cannot be seen. So that is why a meter rule and tape measure would not be able to measure up to 1/10 of a millimeter. Only the Vernier Calipers can measure this. So let's look into the Vernier Calipers in a more detailed way. So this is the Vernier Calipers. In the Vernier Calipers, we have jaws to measure the internal diameter and jaws to measure the external diameter or lengths of objects. For example, this object being measured over here, the diameter is being measured in this object. Now the Vernier Calipers has two scales. One is the Vernier scale and the other is the main scale. This is the main scale and this is the Vernier scale, the small one over here. So we have a screw to tighten the jaws of this Vernier Calipers and this is the main scale. How do we measure using this Vernier Calipers? It is not very difficult. So for example, here I have a Vernier Calipers and this is the object I want to measure using this Vernier Calipers. I open the jaws of this Vernier Calipers and place the object and tighten the jaws around it. Now as you can see, it is written over here that this Vernier scale is calibrated in 0.02 millimeters. So this single mark is equal to 0.02 millimeters. So what would happen is that this one mark represents 0.02 millimeters and 0.04 millimeters, 0.06 millimeters, 0.08 millimeters and 0.10 millimeters is when we get over here. So now we're going to look at the main scale. The reading the main scale shows is we're going to read just beside the 0 of the Vernier scale. This is the marking that is just to the left of 0 and we're not going to go over the 0, we're going to stay behind the 0. So this is 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So 19 millimeters is the main scale reading. So after that we have the Vernier scale. Now there is written that 0.02 millimeter is what each marking of this Vernier scale represents, 0.02 millimeters. So what happens, let me read this Vernier scale. So 0.02 millimeters, 0.04 millimeters, 0.06 millimeters, 0.08 millimeters and then we get 0.1 millimeters. 0.10 millimeters and then we have 0.12 millimeters, 0.14 millimeters, 0.16 millimeters, 0.18 and so on. This is how this Vernier Calipers is calibrated. Now we're going to find a marking of this Vernier scale which is exactly aligned with the marking of the main scale. And so the marking that is exactly aligned with the main scale is this one. What is this marking? How are we going to read it out? So basically this marking over here represents 0.40 millimeters. And then after this marking we have 0.42 millimeters and then this marking is in 0.44 millimeters. So 0.44 millimeters is the vernier scale reading, and 19 is the main scale reading. So when we add this vernier scale reading to the main scale reading, which is 19, we get the answer. And the answer is 19.44. So this is the answer of this vernier calipers. So this is how we use a vernier calipers to measure an object's length or diameter. Basically, read the main scale just to the left of 0 and then the vernier scale. How do we do that? We find the markings of the vernier scale which is exactly aligned with the markings on the main scale. And then we add the vernier scale reading to the main scale reading to find the answer. This is how we use the vernier calipers. So the vernier calipers can be calibrated in many different things. For example, this vernier calipers is calibrated in 0.05 millimeters. So the least count of this vernier calipers is 0.05 millimeters, which means that a single marking of this, which is this one, represents 0.05 millimeters. From 0 to 1 we have 0.10 millimeters. This is how we use our vernier calipers to measure an object's diameter or its length. So now let's go ahead and find out what the zero error is in the vernier calipers. So a zero error is basically what happens is even when the vernier calipers jaws are closed, it shows a reading. If it shows a reading, this means that the vernier calipers has an error. For example, this vernier calipers jaws are tightly closed together and there is no object in between, but it still shows a reading over here. And this reading basically is the zero error. Now, how to read the zero error? In order to measure using this zero error vernier calipers, we would have to know the zero error, and then we're going to find out how we're going to measure accurately with this vernier calipers with it having a zero error. So there are two types of zero error. One is a positive zero error and the other is a negative zero error. The positive zero error is when the zero on the vernier scale is to the right side of the zero of the main scale. And a negative zero error is when the vernier scale zero is to the left side from the zero of the main scale. If the vernier scale 0 is exactly aligned with the main scale 0, this means that the vernier calipers has no zero error. But if it shows something like this, that even when the jaws are closed, tightly closed together and there is no object in between, even if it shows a reading, then it is obvious that there is zero error. If the 0 is onto the left side of the main scale 0, then it is a negative zero error, and if the vernier scale 0 is onto the right side of the main scale 0, then it is a positive zero error. So how do we read this zero error? In order to find out the actual value of this zero error so that we can do measurements from this vernier calipers, we're going to measure the zero error. So let's say, for example, this positive zero error. We are going to find the vernier scale marking which is exactly aligned with one of the main scale markings, which is in this case 6. So this 6 vernier scale marking is exactly aligned with the main scale marking. Now we're going to read the vernier scale from this 0. So we're going to read it from the left side, the way we read it, 1, 2, 3, 4, 5, because it is a positive zero error. So 1, 2, 3, 4, 5, 6. 0.6 millimeter is the positive zero error this vernier calipers has. Now, if I am going to read a negative zero error, then I would read the vernier scale from this 0, from this 10 basically. Not from here, not from this side. I'm going to read it from this side. So it's going to be, this 10 is going to become 0 and 9 is going to become 1. So we're going to read it from this side because it is a negative zero error. If it is a positive one, we read it from here. But if it is a negative one, we read it in reverse. So 0, 1, 2, 3, 4. So 4 in this case is the zero error. Minus 0.4. Remember, always write the minus. Now what will happen is if we are measuring any object using this vernier calipers, this one over here, which has a negative zero error, all we have to do is minus this zero error from the reading the Vernier calipers gives. So if I'm measuring an object and the reading is x, for example, the reading is obviously incorrect because the Vernier calipers has zero error, but all we have to do to make it correct is minus this zero error from the reading it gives. Same with the other positive zero error, we have to just minus the zero error from the reading the Vernier calipers gives and we get the correct reading. So this is how we find the zero error in the Vernier calipers. So now let's look at some examples over here. Here we have some Vernier calipers with their zero errors and their correct readings. So these are the readings. The Vernier calipers over here are shown with the jaws closed. So over here we're going to find out the zero errors of these Vernier calipers, and these are the ones in which they are measuring an object. So they're giving a reading. Obviously the reading is not correct. We have to minus the zero error from this reading and find out the correct reading. So now you can pause the video over here and find out the zero error of this Vernier calipers and do the calculation. Okay, so the zero error of this Vernier calipers is minus 0.03. So because it is a negative zero error, we're going to read it from this zero. So 1, 2, 3 is the markings that are exactly aligned together. So 0 minus 0.03 is the zero error of this Vernier calipers. Now the correct reading of this Vernier calipers here is, first we're going to find the reading of this Vernier calipers that it is showing. So the reading is, the main scale is 0. We're going to find out which of the markings are exactly aligned with the main scale marking, and over here we have 6. So 0.06 is the reading of this Vernier calipers. And now we're going to minus this zero error from this reading. And because minus becomes plus, minus minus is plus, so the answer is going to be bigger than the initial reading. And so the correct reading of this Vernier calipers is 0.09. So this is the correct reading of this Vernier calipers. Now here we have another Vernier calipers with a zero error and reading. So find out the zero error and correct reading. So the zero error of this Vernier calipers is 0.03. Because it is positive, we start from here 0.1, 0.2 and 0.3 exactly aligned. So how we're going to find the reading of this Vernier calipers? We first find the main scale reading, which is 1 millimeter. So there we have the main scale reading. Then we're going to find the Vernier scale reading, which is 0.06 millimeters. We're going to add these two readings, 0.06 with 1, and we get 1.06, which is the reading of this Vernier calipers. So this is the reading of this Vernier calipers, and now we're going to subtract the zero error from this reading to find the correct reading, and the answer is 1.03. So this is the correct reading of this Vernier calipers. Now here we have another Vernier calipers. Pause the video and find out the zero error of this Vernier calipers and the correct reading as well. This is a negative zero error. So the answer is minus 0.06. Minus 0.06 is the zero error of this Vernier calipers. The correct reading is 6.4 is the main scale reading of the Vernier calipers, and the Vernier scale reading is 0.03. So we're going to add this Vernier scale reading to the main scale reading. 0.03 plus the main scale reading, and the answer is 6.43. Now we're going to subtract this zero error from this reading, and the answer is 6.49. So this is how we find the zero error of a Vernier calipers and how we correct the reading of the Vernier calipers. Now that we've understood the Vernier calipers and the zero errors and how to find the zero error and correct the given readings with the zero error, we can now move ahead onto the micrometer screw gauge. So the micrometer screw gauge measures accurately up to 1 million part of a meter, that is a micrometer. If we divide a meter into 1 million parts, we get a micrometer. And a screw gauge measures accurately up to a micrometer. So it is even more accurate than a Vernier Calipers. So this is what a screw gauge looks like, micrometer screw gauge. Let's go into a much more detailed version of the micrometer screw gauge. So here we have the measuring faces of this, the anvil and the spindle, and this is the U-frame. These are the jaws basically of this micrometer screw gauge. Then again, the micrometer screw gauge also has a main scale and a fractional scale which is on the rotating barrel. This is the symbol and the ratchet stop. This is used to apply just the right pressure onto the object being measured. Here we have this micrometer screw gauge. Now, how do we read the micrometer screw gauge? The micrometer screw gauge also has a main scale and a fractional scale. So, the main scale tells us the measurement in millimeters, and the fractional scale tells us a fraction of the millimeter that we have to add in the main scale reading. So, for example, this, even though it's not measuring any object, for example, it is measuring an object because it is still open, it's not closed. So, this micrometer screw gauge has the main scale reading shown like this. So, the reading is something like this: 0, 1, 2, 3, 4, 5. So this is 5 millimeters. 0, 1 millimeter, 2 millimeter, 3 millimeter, 4 millimeter, 5 millimeter, 6 millimeter, and 7 millimeter is the point where it ends. So 7 millimeter is the main scale reading. Then we have to look at the fractional scale. The marking of the fractional scale that is aligned with this line is 75, as it can be seen. Now this 75 is written as 0.75. If the number is in tens, then we say 0.75, and if the number is in units, then we say 0.01 or 02 or 03. So 0.04 or 0.06. But if it's in tens, then we write it this way: 0.75. No zero in the middle. No zero after the point. So now we add the main scale reading and the fractional scale reading to get the answer, which is 7.75. So this is how you measure an object's length or diameter using the micrometer screw gauge. So let's do an example over here. What is the reading this micrometer screw gauge shows? So the main scale is this one, and it is calibrated something like this: 50, and the upper dots basically represent 0.5. So if this is 50, then the upper dot will be 50.5, and then this one is 51, and then we have 51.5, then 52, 52.5, 53, 53.5, 54, 54.5, and 55. So this is how we do it. Now this is 60, and the main scale is ending at this point, which is 60.5. So the main scale reading is 60.5. Let's write it down here. This is the main scale reading, and the fractional scale reading is, this is 10, 11, 12, 13, 14, 15, and 16. So the fractional scale reading is 16, so it is 0.16. So we add 0.16 in the main scale reading and we find the answer, and the actual reading is 60.66. So this is how we measure using a micrometer screw gauge. The main scale is calibrated in millimeters and 0.5 millimeters, something like this. So this millimeter is 1 millimeter and that one is 0.5. So if 50, that mark would represent 50.5. Then the fractional scale tells us the fraction of a millimeter that we have to add in the main scale reading. So now let's move ahead onto the micrometer screw gauge zero error. Again, the zero error occurs when any instrument shows a reading even when its jaws are completely closed. If a micrometer screw gauge doesn't have a zero error, it will look something like this: that the fractional scale 0 would be completely aligned with the main scale 0. But if it has a zero error, then the two zeros will not be aligned. Same as Vernier calipers, the micrometer screw gauge also has a positive zero error and a negative zero error. Positive zero error is when the zero on the fractional scale is lower than the zero on the main scale. And the negative zero error is when the zero on the fractional scale is above the zero on the main scale. Something like this. So this is a positive zero error and this is a negative zero error. So we know that this is positive and negative. Now let's read the zero error. Read the value of the zero error so that we can make measurements using this micrometer screw gauge. What is the zero error of this micrometer screw gauge? All we have to do is read the markings to where the zero is coming from. So if it's a positive zero error, we're going to read from this zero. In micrometer screw gauge, we always read the zero error from the fractional scale 0 towards the main scale 0. So if it's a positive zero error, we will read it like this: 0, 1, 2. So positive 0.02 is the zero error of this micrometer screw gauge. But over here it's a negative zero error, but still we will just read from the fractional scale 0 towards the main scale 0. So in this case we will be reading backwards in a way. So this negative zero error is not going to be called 46. It is going to be 0.04, because we're going to read it backwards because it is a negative zero error. So in other words, a micrometer screw gauge zero error is supposed to be read from the fractional scale 0 towards the main scale 0, whether it is a positive zero error or a negative one. So if it's a negative one, we will basically read backwards from this 0 towards this 0. Something like this. Not going to read it all the way around to 46. It's not going to be 46, it is 0.04. The zero error is 1, 2, 3, 4. 0.04 minus 0.04. Because it is a negative zero error, so we write the minus sign. So this is how you read a zero error. So let's do some examples here. So this is the zero error and this is the reading of this micrometer screw gauge. Now first of all, we're going to understand whether this micrometer screw gauge has a zero error or not. Of course it has zero error because the lines are not aligned together. And what is the zero error? Is it a negative zero error or a positive zero error? Yes, it is a negative zero error because the 0 is above the main scale 0. The 0 on the fractional scale is above the main scale 0. So it's not below, but it's going above. So we're going to write down the zero error. What is the zero error? It is 0.01. Because of course the distance is of only one marking, so the zero error of this micrometer screw gauge is minus 0.01. So this is the zero error. Now here we have the reading of this micrometer screw gauge. So what is the reading? Firstly, we're going to read out the reading and then correct it. So the reading is 0, 0.5, 1, 1.5, 2, 2.5, 3, 3.5, 4, 4.5 and 5. So the reading is 5. This is where the main scale is actually ending. So the reading of the main scale is 5 and the reading of the fractional scale is 20, 21, 22, 23. 0.23 is the reading on the fractional scale. So we're going to add these two readings and we get the answer, which is 5.23. So this is the reading of the micrometer screw gauge, but it is not a correct reading because the micrometer screw gauge itself has a zero error. So in order to correct this reading, we will minus this zero error, just like we did in the Vernier calipers. So we minus and we minus the zero error, which is minus 0.01. Always remember to put brackets, because if we are minusing it, we will put two minus signs. So we have to put a bracket in between in order to make this a separate value. So when we do this, the minus basically become plus. So the reading is higher. So don't confuse this, because in maths, minus is equal to plus. And the answer is 5.24. So the correct reading is 5.24. So I hope now you've understood the zero error and the way we calculate the zero error and subtract the zero error from the readings that we get from a micrometer screw gauge which has zero error. So if the zeros are aligned together, there is no zero error. If they are not aligned together, there is a zero error, and if the fractional scale 0 is lower than the 0 on the main scale, then it is a positive zero error, and if it is above the 0 on the main scale, it is a negative zero error. And we will just basically count the markings from the fractional scale 0 to the main scale 0. If it is a negative zero error, we count it backwards. If it is a positive one, we count it the right way. Then we correct the reading of such a micrometer screw gauge by minusing the zero error from it. So this was all about micrometer screw gauge and the Vernier calipers. I hope it was very clear, because the Vernier calipers and micrometer screw gauge are very precise and accurate. So now that we've understood the instruments we use to measure length, we can now move ahead onto the instruments we use to measure volume. So the SI unit of volume is the centimeter cube, cm cube. The tools we use to measure volume of regular objects are the Metre Rule, tape measure, micrometer screw gauge, and Vernier calipers, all of which we use for measuring length as well. And the tools we use to measure the volume of liquids and gases are the measuring cylinder, volumetric flask, beaker, burette, and pipette. Burette and pipette are used to measure small and accurate values. And the tools we use to measure the volume of irregular objects, we use the measuring cylinder and water method. Let me explain this in a moment, but let's first understand how we measure the volume of regular objects. So the equation we use for measuring the volume of irregular objects is this: length multiplied by height multiplied by width, and we get the answer in cm cube. All of these are supposed to be measured in centimeters so that we get the answer in centimeter cube. Okay, so this equation only applies to the objects which have a regular shape, such as this cube. But if we have a different object, so this equation only applies for regular objects like the cube. This equation, we can't apply this equation for measuring the diameter of a golf ball. For doing this, we will use the instrument which is the Vernier calipers or the micrometer screw gauge, any which will work. But the Vernier calipers would suit this because a golf ball is not very small. Micrometer screw gauge measures very small quantities. But because this golf ball cannot be measured using a meter rule or a tape measure, so we use the Vernier calipers as it has jaws. So we measure this golf ball while using the Vernier calipers. It tells us the reading of the diameter. But for measuring the volume of a regular object like a cube, we use this equation: length into height into width. And all these quantities are supposed to be taken by a meter rule or a tape measure. If the cube is small, very small, then we use a micrometer screw gauge or a Vernier calipers. So now, the tools we use to measure irregular objects, such as this rock over here, is a measuring cylinder and water. So I want to measure the volume of this rock, but I can't use any kind of instrument because it is not regular in shape. It is neither a cube or a spherical object, but it is irregular in shape. So to measure the volume of this object, what I will do is take a measuring cylinder and add water in it. Now we note the volume of the water the measuring cylinder shows, which is 200 ml right now. So I note this volume down, and then I immerse the rock that I'm going to measure the volume of. After immersing the rock, I take the value of the water again, which is now 300 ml. Now I subtract the previous reading of the water from the initial reading to find the volume of the stone, which is 300 minus 200 is 100. So the stone's volume is 100, and we can convert this ml into centimeter cubes as well. So this is the method we use to measure the volume of irregular objects. Now here are the apparatus we use to measure liquids and gases. So the beaker measures approximate volumes. A measuring cylinder is accurate to the nearest centimeter cube. Now remember, whenever we measure volume with the measuring cylinder or any kind of these instruments, we always read off the volume with the eye level at the bottom of the meniscus, never at the edge of the meniscus because it has an inward dome shape. So we always read the bottom of the meniscus. Then we have the burette, which is accurate to the nearest 0.1 centimeter cube. The volume of liquid required is run off from the bottom through a tap. This is the tap. Then we have the pipette. A pipette measures fixed volumes such as 25 centimeter cube, 50 centimeter cube or 10 centimeter cube very accurately. Then we have the volumetric flask. So the volumetric flask measures fixed volumes when making up solutions of exact concentrations. Fixed volumes such as 100 centimeter cube, 250 centimeter cube and 1 dm cube. So these are the apparatuses we use to measure liquids and gases. Now let's move on to understanding density. After mass, length and volume, we are now on density. So density is a measure of how much mass is contained within a given volume of a substance or object. So if there is a given volume, such as this object has a volume, density is a measure of how much mass is contained in this volume. And a density, an object's density can never be predicted because we can never predict how much mass there is in a specific volume. So there is a box of chocolate, for example, which is big in size, but when we hold it, it is light. Its weight is light, which means that the box doesn't have much mass. It has less mass than its volume. So the equation for density is equal to mass divided by volume. Just like we read in the beginning of when we were reading base units and derived units, I said this equation. Mass divided by volume, gram divided by cm cube, and we get gram per cm cube, which is the density's unit of measurement. Okay, so this is an equation. Now this equation cannot only be used for density, it can also be used to measure volume or mass. With any two of these quantities, we can measure a single quantity. For example, we divide mass with volume and get density. And if we want to measure volume, what would we do? Would we divide density by mass or mass by density, or would we multiply these things? To remember this, I have made this triangle over here. So this is how we write the equation in triangle. So because mass is upon volume, so we write mass above and volume below. And density is multiplying by volume. Now for example, I am given the density and volume of an object and I want to find out the mass. What would I do with the density and volume? All we have to do is just hide the mass over here, and what we get is volume multiplying density. So if we multiply volume by density, we will get the mass. Remember, we're not going to divide it. So this is the difference. This is how we rearrange the equation to find another physical quantity. So now if I want to find the volume of an object, I would simply hide the volume over here, and what I get is mass dividing by density. So if I divide the mass of an object with its density, I will find the volume of it. So this is how we use this triangle for rearranging the equation. So here are some points to remember about density. Number 1, volume is inversely proportional to density, which basically means is that when volume increases, the density decreases, and when volume decreases, the density increases. Only if the mass is kept constant. So if an object's mass is, say for example, 50 grams, so if the volume would be small, the density of the object would be more. And if the volume would increase and the mass would remain the same, 50 grams, the density would decrease because the amount of matter in this space, say for example, this is the volume of an object and it has the mass 50 grams. Now of course, If the volume of the object doubles up and the mass remains the same, then there is less mass in this space. Whereas in this space, the mass is more concentrated. So when the mass is concentrated, the density is more. But over here, it is not very concentrated, so the density decreases. So volume is inversely proportional to density only if the mass is constant. If the mass will also increase with the volume, then this rule will not apply. So if the mass is kept constant, when volume increases, the density decreases. And when volume decreases, the density increases. Basically, the mass per unit meter increases because the particles get more concentrated in a small space compared to a larger space. So the density increases if the volume decreases, and it decreases if the volume increases. The second point to remember is that objects less dense than water float, and those with a higher density than water sink. Say for example, icebergs float on water. This is because ice is less dense than water. The structure of ice is more open than the structure of water. So the particles in the water are close together compared to the particles in ice. So because of that, there is less mass in the unit volume compared to the water. So that is the reason why icebergs float on water, because the density of icebergs is less than water. Any object which has a higher density than water sinks. So this was all about density, volume, the instruments we use for measuring these objects, these physical quantities like the micrometer screw gauge, the Vernier calipers, the tape measure, the meter rule. We have completed the first chapter of our physics O-level lesson. Now let's have a small quiz of this chapter. We have some past papers MCQs related to this chapter we just read right now. So let's start with this question. I will ask you to pause the video after I read the question so that you will find the answer first and write it down. And then play the video when I give you the answer. Check the answer if it is correct or not. So the question is, a student collects some stones and finds their density. Which apparatus is needed to measure the mass and the volume of the stones? So here we have 4 options A, B, C and D. Pause the video and write down the answer which you think is correct. So the answer of this question is D. Option A is incorrect because mass cannot be measured using a Vernier calipers and the volume cannot be measured using a pan balance. The second option is also incorrect because the mass can be measured using a pan balance, but the volume of stones cannot be measured using a screw gauge because stones are irregular in shape. The mass in option C can be measured using a pan balance, but again the volume cannot be measured using a Vernier calipers. So option C is also incorrect. Lastly, we have option D, in which the mass is being measured with a pan balance and the volume is being measured with a measuring cylinder and water. So this option is correct because the volume of stones which are irregular in shapes can only be measured using the measuring cylinder plus water method. So option D is correct. Second question. An object is weighed on Earth and its mass is also measured. The object is then weighed on the Moon and its mass is also measured. So how do the values of the mass and weight change? So there is an object which is weighed on Earth and its mass is measured. Then the mass and the weight of the object are measured again on Moon. So how do the values of the mass and weight change? Here we have the options A, B, C and D. So the first option is mass decreases and weight also decreases. Second option is mass decreases, weight stays the same. The third option is mass stays the same and the weight decreases. The fourth option is that the mass stays the same and the weight also stays the same. Which option is correct? Option C is correct. How? Because we know that the mass of an object never changes, whether it's on Earth or on any other planet or even in space. The mass of an object stays the same, whereas the weight of an object can vary. Because the weight is a force, the weight is basically a measure of the Earth's gravitational force. So the Earth's gravitational force is more than the gravitational force on Moon, so that is why the weight will decrease on the Moon. And in space there is no force acting on the body or an object, so that there is no weight of an object, but still the mass never changes. The mass always stays the same. So option C is correct, that the mass stays the same and the weight on the Moon decreases. First option is incorrect because the mass never changes, so mass cannot decrease, whereas weight can decrease. Second option is also incorrect because it's also saying that the mass decreases and weight stays the same. Weight doesn't stay the same. Weight can vary, but the mass can never change. The fourth option is also incorrect because weight doesn't stay the same. So the correct option is that the mass stays the same and the weight decreases because the gravitational field strength of the Moon is weaker than the gravitational field strength on Earth. So that is why the weight decreases. Second question. The density of the block is 2.5 grams per centimeter cube. What is the mass of the block? Here we have the options. What is the correct answer? Pause the video and do your calculation and find the answer. So the correct answer is 150 grams. How is that possible? Because over here we're asking what is the mass of the block. And we are given the density of the block, but not the volume. But we can measure the volume using the lengths of the volume given. So the width, length and height of the block is given over here. So when we multiply these values together, 5 by 4 by 3, we get the volume of the block. So then when we multiply the volume with the density, we get the mass of the block. We basically derive the density is equal to mass upon volume equation. So when we want mass, we hide the mass. What we get is volume multiplying by density. The volume of regular objects is measured with the length into width into height. So we're given all the values over here. When we multiply them and then multiply the volume of this block with its density, we get the mass of the block, which is 150 grams. Now the second question. A quantity is quoted as having a value of 6.2 ms. In what unit is it measured? Here we have the options. Pause the video and find the answer. So the correct answer is D. The unit is milliseconds. So if we were thinking it's meters, of course not. It's not meters because the symbol for meters is M, small m, just M. There's no S. And if we think it was meters per second, that is also incorrect, but because meters per second is written as m/s. So this is only ms. It is not m/s. Meter per second is m/s. Then we have microseconds, which is also incorrect because microseconds is written as mu and s. Mu is a symbol which we use for micro, and m is a symbol which we use only for meters or milli. So microseconds is also incorrect. And then we have milliseconds. Of course it is milliseconds because m is the prefix we use for milli. So the last option we get is milliseconds, which is the correct answer. ms represents milliseconds, not meters per second, because meter per second has a slash in between the m and s. If we say per second, then it means that it is dividing. So meters dividing by second. So there is always a slash in between the meters and second. The next question. A measuring cylinder contains 20 cm³ of water. A stone is placed in the water and the water level rises to 83 cm³. What is the volume of the stone? Pause the video and find the answer of this question. So the correct answer is 18 grams. Option A. So we read before, to measure the volume of an irregular object, which is the stone in this case, we use a measuring cylinder plus water method. And how do we use that method? We first add the water and note down its volume, which it says is 20 centimeter cube. Then after the stone is placed, we get the water level, which is risen up to 38 centimeter cube. So to find the volume of the stone, we subtract the previous reading of water by the initial reading with the stone placed in, and we get the volume of the stone, which is 18 grams. It is not 50 or 24 or 150 grams, it is 18 grams. So this is the correct answer. Next question. Which instrument is most easily used to measure the internal diameter of a pipe? Pause the video and find out the answer. Of course, the answer is Vernier Calipers, because only the Vernier Calipers has jaws to measure an internal diameter. Micrometer screw gauge cannot measure internal diameter of a pipe, neither can a measuring cylinder or a manometer. Vernier Calipers is the right choice because it has jaws which measures the external and internal diameter of a pipe. Next question. A Vernier Calipers reads to 1/10 of a millimeter. Which reading shows this precision? Find out the answer. So the correct answer is B. So to understand this, when we convert these centimeters into millimeters, we get this. The 3.3 centimeters becomes 33 millimeters. Then the second option becomes 33.1 millimeters. And the third option becomes 33.10 millimeters. And the fourth option becomes 33.12 millimeters. So 33 millimeters is a measurement which is correct up to 1 millimeter. The second reading is correct up to 0.1 of a millimeter, that is correct to 1/10 of a millimeter. So the third and fourth readings are correct up to 1/100th of a millimeter, which is 0.01 of a millimeter. So these are also not correct. Another way to understand this is when we use a micrometer screw gauge to measure an object's length, the fractional scale always shows us the measurement in centimeters. And how do we read these centimeters over here? As you can see, we always say 0.45, and if it is like written something like this, then we say 0.05. The fractional scale basically tells us the 1/10 of a millimeter in centimeters. So this is another way we can understand that the correct answer is 3.31 centimeter. Okay, next question. A plumber measures as accurately as possible the length and internal diameter of a straight copper pipe. The length is approximately 80 cm and the internal diameter is approximately 2 cm. What is the best combination of instruments for the plumber to use? We have the options written down here. Pause the video and write down your answer. So the right answer is C. Okay, this is the correct answer because of course the internal diameter of a pipe cannot be measured using a rule. So these two options are cancelled obviously because they have internal diameter which is being measured with the rule. This is not correct. Only the Vernier calipers can measure the internal diameter with its jaws. We are then left with option C and D. So option D has the length which is being measured by a tape measure. So a tape measure is used to measure very long lengths. A rule can measure up to 1 meter. Because of course if we write down a rule, we would expect the rule to be a meter rule. So the length of the copper pipe is 80 centimeter, which is less than 1 meter. So a rule can easily measure this length. A tape measure would be not suitable for it, as a tape measure is used to measure longer lengths like 2 meters, 3 meters and in kilometers. So Tape measure is used when the length of any object is greater than 1 meter. So the length of this straight pipe was 80 centimeter, and this can easily be measured using a meter rule. So the correct option is C. So these were all the questions. This was the first chapter of our physics O-level lessons, measurements and units. We have completed this chapter successfully and also have done questions related to it. So let's summarize some of the stuff we learned in this chapter. Starting from the beginning, we learned what physical quantity was. Then we understood what measurement is. We then understood units of measurement, the SI system of units, the base units in the SI system, and the derived units in the SI system, and the metric system of units, which includes prefixes, which we learned as well. Then we understood the conversion of units. For that, we understood the conversion factors and memorized them, and we understood the one-step conversion and two-step conversion, the equations we use to convert. After that, we understood what mass is, the SI base unit of mass, some important notes to remember, and the instruments we use to measure mass. Then we understood time, base unit, the SI base unit of time, and the instruments we use to measure time. Then we learned about length, the SI base unit of length, and the tools we use to measure length. We then went into detail of the tools we use to measure length. We understood the meter rule, how accurately the meter rule can measure up to, and how do we measure an object's length using a meter rule. Then we understood tape measure. And then we understood the Vernier Calipers. What is the smallest length the Vernier Calipers can measure? It can measure internal diameters and external diameters. We went into detail how we measure using the main scale and vernier scale of the Vernier Calipers. Then we understood the zero error of the Vernier Calipers. Positive zero error and negative zero error. How we can find out the zero error and find out the correct readings of the Vernier Calipers. Then we understood the micrometer screw gauge, the smallest value a micrometer screw gauge can measure. This is the mu sign. This is the sign of micrometer. We understood how we use the main scale and fractional scale of the micrometer to measure. The equation of micrometer screw gauge. Did some calculations and found and understood the zero error of the micrometer screw gauge, the positive zero error and the negative zero error, and how we can correct the reading of such a micrometer screw gauge. Then we understood the volume, the SI unit of volume, and the tools we use to measure the volume of regular objects, of liquids and gases, and of irregular objects. We use the length into height into width equation to measure the volume of regular objects, and we use some instruments to measure the volume of regular spherical objects. Then we understood how we use a measuring cylinder and water to measure the volume of irregular objects. The apparatus we use to measure liquids and gases, the volume of liquids and gases. And then finally, we understood density, the equation for density, some points about density that we had to remember. And then we did past paper MCQs relating to this chapter. So this was all about this chapter, measurements and units. I hope you have understood this clearly and would practice all the equations and memorize the points and tables I've given in this chapter, like the conversion factors, the points about density, mass, and volume, and the equation we use to measure density. These questions would help you to understand and memorize these points faster. So thanks for watching this video, and I'll see you in the next chapter.